Picture a black hole 2.5 billion times the mass of our sun. Now, stop picturing it as a drain, because the one we're opening with today isn't just swallowing, it's blowing. And the blast it drives reaches across 300,000 light years, stirring an entire cluster of galaxies.
300,000 light years? That's roughly 3 times the width of the Milky Way, the reach of a single black hole.
That's our lead. Then, dead stars that hide their meals, a metal world mission using Mars as a rehearsal studio, and the growing problem of traffic on the road to the moon.
And because it's the 30th, there are 2 meteor showers peeking over your head tonight. We'll tell you exactly where to look north and south.
It's Thursday, the 30th of July, 2026. I'm Anna.
And I'm Avery. This is Astronomy Daily.
So let's start with a question that sounds simple and isn't. What does a black hole actually do to the space around it?
The cartoon answer is, it eats. Anything that gets too close falls in and never comes back.
Right, and that part's true, but it's only half the story. When a supermassive black hole is feeding hard, it doesn't swallow everything cleanly. It's a messy eater. Enormous amounts of energy pour out of the region around it, radiation and powerful outflowing winds of gas. And astronomers have a name for the way those winds push back on the wider universe. They call it feedback.
Feedback, as in the black hole feeds and the galaxy gets a response.
Exactly. And it matters enormously because feedback is one of the ways galaxies keep themselves in check. Here's the puzzle it solves. At the center of a big galaxy cluster, there's a huge reservoir of hot gas, millions of degrees, glowing in X-rays. By all rights, that gas should be cooling, sinking to the center and collapsing into vast numbers of new stars.
And it doesn't.
And it doesn't. These cluster cores are far quieter than the simple physics predicts. Something is reheating that gas, keeping it stirred up, stopping the runaway cooling. For years, the leading suspect has been the central black hole, that its outbursts dump energy back into the gas and hold the whole system in balance. But there's been a stubborn gap in the evidence.
Which is?
We could see black holes driving winds on the scale of their own galaxy. What we couldn't show was those winds reaching much beyond the galaxy, out into the space between galaxies, on the scale of the whole cluster. That's the part that stayed theoretical, until this study.
So who did it and how?
A team led by Satoshi Yamada at Tohoku University in Japan, with colleagues from Kanazawa, Tokyo Metropolitan, and Kyoto universities. It's published in Nature Astronomy this week on the 28th. And their target is a genuinely special object, a quasar called H1821 plus 643.
Quasar meaning a black hole that's feeding so ferociously it outshines its entire galaxy.
That's it. Some of the most luminous single objects in the universe. This one sits in the constellation Draco, about 3.4 billion light-years away, and its black hole weighs in around 2.6 billion solar masses. But here's what makes it the perfect laboratory. It's the nearest quasar that lives right at the heart of a galaxy cluster. So you've got a raging black hole and a giant reservoir of hot cluster gas in the same place close enough to study in detail. That almost never happens.
And to study it, they used XRISM, which longtime listeners will remember.
We've talked about it before, yes. XRISM, the X-ray Imaging and Spectroscopy mission, is the Japanese-led X-ray observatory with NASA and the European Space Agency aboard. And its superpower is a kind of spectroscopy so precise it can read the motion of hot gas from the light it gives off.
Explain how that works, because this is the clever bit.
It is. The hot gas in a cluster contains iron atoms, and those iron atoms emit X-rays at very specific, sharp energies, like a particular note. Now, if that gas is churning and swirling, some of it moves towards us and some away. And just like a siren changes pitch as it passes you, the motion smears that sharp X-ray note out. It broadens the line. Measure how broad the line is, and you've measured how violently the gas is moving.
So the iron lines become a speedometer for gas you can't otherwise see.
A speedometer for turbulence. And when they pointed XRISM at H1821 plus 643 and read those lines, the gas was far more turbulent than anyone expected. Compared with a calm, well-behaved cluster like Perseus, the motion here is dramatically more violent, and it's violent across a huge span of space.
How huge?
The disturbance reaches out to something like 300,000 light years from the black hole, well beyond the host galaxy, out into the cluster itself. And the energy tied up in that turbulence is on the order of 100 times greater than earlier estimates.
100 times? So this isn't a tweak to the model, it's a different order of magnitude.
It really is. What they've shown is that this black hole is pumping something like a few to 10% of its radiative energy straight into the surrounding cluster gas on scales of tens to 100 kiloparsecs. That's the missing link. That's direct evidence of a black hole heating and stirring its cluster from the inside. Exactly the process theorists needed to explain why all that gas isn't collapsing into stars.
Yamada had a nice way of putting it, didn't he?
He did. He said black holes are famous for sucking matter in, but they also eject gas in powerful winds. And this study says those winds are immensely stronger than we understood. For the first time, he says, we've shown a black hole influencing the broader cosmos through a shockwave of astonishing power.
And the reason to care, beyond, wow, big number, is that this is really a story about how galaxies grow up.
That's the heart of it. Black holes and their galaxies grow together, and feedback is the thermostat. Too little, and the gas cools, and the galaxy makes far too many stars. Too much, and it blows the fuel away, and star formation shuts down. Get it right, and you build the galaxies we actually see. What Yamada's team has done is catch that thermostat in the act, working on a scale we could only assume before, moving energy and eventually the chemical elements forged in stars out across the cluster.
A black hole redecorating a whole neighborhood it never touches directly.
More than 3 times the width of the Milky Way from a single point at the center. And this is really just the opening chapter. XRISM is still young, and objects like H1821 plus 643 are rare and precious. Expect more of these hot cluster cores to get the same treatment, and expect our picture of how black holes shape the universe to keep getting bigger, which is a lovely irony, isn't it? The more we look at the objects famous for pulling everything in, the more we find them reaching out.
Reaching out. Good place to leave the giant. Let's bring it right down to a single dead star and a mystery about what it's been eating. So, story 2. A white dwarf is what our sun will become, billions of years from now, the burnt-out, Earth-sized core left behind when a star like ours runs out of fuel. And for a long time we've known these dead stars are a bit macabre. They're surrounded by the shredded remains of their old planetary systems, asteroids and even planets torn apart and pulled in.
The star literally raining its old planets down onto itself.
Beautifully grim, yes. We can tell because we see the metals from that debris polluting the star's atmosphere. But new research says we've been undercounting the meal, that white dwarfs are eating far more planetary material than we thought, and the reason we missed it is magnetism.
Magnetic fields hiding the evidence.
Exactly. Some white dwarfs are strongly magnetic, and when debris falls in, those magnetic field lines funnel the infalling material down to the star's magnetic poles, concentrating it into small patches instead of spreading it evenly. And patches at the poles are much easier to miss.
And here's the part I love. The researchers point out it's essentially the same physics as an aurora.
It is. Think about how our own auroras work. The sun throws charged particles at Earth, they follow our magnetic field lines down to the poles, and they light up a glowing patch in the atmosphere. On a magnetic white dwarf, swap the solar particles for the debris of a dead planetary system, and you get the same choreography. Material guided along field lines to a bright spot at the pole.
An aurora made of ground-up planets.
On the corpse of a star. And the practical upshot's real. If this magnetic funneling is common, then a lot of white dwarfs we've written down as clean may actually be feeding, just quietly, in a way our surveys don't catch, which changes how we estimate what these old planetary systems were made of.
A window into the guts of dead solar systems, including one day our own. Speaking of dress rehearsals for the future, let's go to Mars. Story 3. NASA's Psyche spacecraft is on its way to one of the strangest targets in the solar system, the asteroid 16 Psyche, a world that may be the exposed metal core of a shattered baby planet. Mostly metal, not rock or ice. We've never visited anything like it.
And it doesn't get there until 2029.
Not until 2029, that's right. But on the way, back in May, it swung past Mars for a gravity assist, using the planet's pull to bend its path and pick up speed for free. And NASA's just shared what the team did with that flyby, which is the fun part. They treated Mars as a rehearsal studio.
A chance to switch everything on and check it works far from home.
Exactly. They put the cameras, the magnetometer, and the particle instruments through their paces against a real world instead of empty space. They captured a striking time-lapse of Mars sliding by. They even picked up neutrons coming off the planet. But the detail that jumped out at me, the imager managed to pick out Phobos and Deimos, the two tiny moons of Mars, from a great distance.
The little Martian moons, and that wasn't just for a nice photo.
No, that was the whole point. Spotting two small, faint moons against the glare is exactly the kind of needle in a haystack test they'll need when they arrive at asteroid Psyche and go looking for any little moonlets orbiting it. So Mars became a practice run for a search they'll do for real in a few years' time.
Rehearsing the hard shot on a target you already know, so you're ready for the one you don't.
Precisely. Every instrument checked, calibrated, and confident, 3 years before it matters. From one careful mission to a much messier problem closer to home, Avery, the traffic on the road to the moon.
Story 4. We spend a lot of time on this show talking about who's going to the moon. NASA's Artemis program, China and Russia's planned research station, Europe's Argonaut landers, and a growing crowd of commercial missions. The next decade could see dozens of flights into what's called cislunar space, the whole region between Earth and the moon.
And everywhere we've ever gone in space, we've left junk behind.
That's the worry. We've made low Earth orbit crowded and cluttered. The question this new study asks is, are we about to do the same thing to the road to the moon before we've even properly moved in? It's from a team at the Chinese Academy of Sciences, and they've looked at a specific, clever kind of orbit out there, a distant retrograde orbit.
Which is one of those very stable parking spots in the Earth-Moon system.
Right, a wide, stable loop that's attractive precisely because spacecraft can sit in it for a long time without much fuel. The catch is, if a spacecraft in one of those orbits breaks up, an explosion, a collision, the debris doesn't just fall away and disappear the way it might near Earth. The team modeled how those debris clouds spread, and out there, the fragments can linger and drift in ways that are genuinely hard to predict.
And unlike low Earth orbit, there's no friendly atmosphere out there to eventually drag the rubbish down and burn it up.
That's the crux of it. Near Earth, the atmosphere slowly cleans up after us. In deep cislunar space, there's no such janitor. Debris can stay a hazard far longer. So the value of work like this is that it's preventative. If we can map where the risky orbits and the lingering debris clouds are before the traffic arrives, we can design missions to steer clear and maybe keep the highway to the moon open for everyone who wants to use it.
Cleaning up before we make the mess, for once. Now, let's get you outside, because tonight the sky is putting on a show, and this one is genuinely for tonight, wherever you're listening. 2 meteor showers are peaking at the same time, the night of the 30th into the early hours of the 31st. The southern Delta Aquariids and the Alpha Capricornids.
2 at once. Tell us the difference between them.
They've got very different personalities. The southern Delta Aquariids are the steady workhorses. More meteors, a bit fainter, radiating from the constellation Aquarius. Their parent is thought to be a comet called 96P Machholz. The Alpha Capricornids are the opposite. Not many, but the ones you get are slow, bright fireballs, real showstoppers, coming from the direction of Capricornus from a comet called 169P Meet.
So quality versus quantity, sharing the same night.
Exactly. Now, the honest catch this year, the moon. We had the full buck moon just last night, so tonight it's still around 98% lit, and that glare will wash out the fainter meteors. But, and this is the saving grace, those bright Capricornid fireballs can punch right through moonlight. As one astronomer put it, one bright one is worth 20 faint ones.
So how do people actually watch? And this is where North and South really differ.
It does, so let's do both properly. First, the good news for us here in the Southern Hemisphere, this is our show. Both radiants ride high overhead from southern latitudes, so we get the best seats. The southern Delta Aquariids can deliver something like 10 to 20 an hour from a dark site under a better moon. And even tonight, with the moon bright, the south still comes out ahead.
Cygni and the East Coast? When and where?
Head out after the moon and sky settle, late evening onward, but the best window is the small hours local time, roughly 1 to 4 a.m. when the radiants are highest. Look towards the north and east, get as far from city lights as you can, and give your eyes a solid 20 to 30 minutes to adapt. Lie back and take in a wide patch of sky rather than staring at one spot.
And for our North American listeners, our biggest audience, who don't get the radiant as high,
you can still absolutely catch this. You just work with lower numbers and lean on the fireballs. Your best time is also the pre-dawn hours. Think 2 to 4 a.m. local, whether that's Eastern, Central, Mountain, or Pacific time, once the radiants have climbed as high as they'll get. The pro tip for the moonlight, position yourself facing away from the moon, with it at your back or blocked behind a building or a hill, so its glare isn't in your eyes. Then watch a broad stretch of sky and wait for those slow Capricornid fireballs.
no telescope, no binoculars.
Done it all. Meteors are a naked eye, whole sky event. Just you, a reclining chair, something warm, and patience. And if tonight clouds you out, both showers stayed active for another week or two, so you'll get more chances as the moon thins out and conditions improve.
2 comets worth of dust burning up over your head. Not a bad way to end the day.
Not bad at all. Look up if you can.
That's the lot for today. Every story with links and sources is over at astronomydaily.io. The news site has the full back catalog, a rolling news feed, and you can sign up for the newsletter or drop us a line right there.
We love hearing from you. Tell us if you catch a Capricornid fireball tonight. Find us at Astro Daily Pod and on the Bytes.com podcast network.
For Anna and for me, thanks for listening.
Until tomorrow, clear skies.
Astronomy.